afternoon to everybody. So this is in principle the continuation of the course that we started last week, but since I know that there are some new people in the audience and some old people in the audience, so what I'm trying to do is I chose the topic for today, which is self-contained, so you'll be able to follow. But I want to first spend the first few minutes adding something I wanted to say at the end of last class. So for the new people, you have to be patient for a bit. And also let me recall you the topic of this lecture. We are discussing various examples of parabolic flows for which there is some slow form of butterfly effect or slow form of divergence of nearby trajectories. And we saw that there are various families of examples that I mentioned last time. So I'll recall you the horocycle flow on a constant negative curved surface. And more in general, you could look at unipotent flows, which generalize this example to Lie groups. So this is on unit tangent bundle of a hyperbolic surface, and this is on some G mod gamma ut, and their time changes. And it's very important, as we saw last time, to consider time changes because they give many more examples of parabolic flows. And then we saw nil flows on nil manifolds and their time changes. And as a special case, we discussed last week Heisenberg nil flows, and we'll go back later probably tomorrow. We'll say something more about another aspect of Heisenberg nil flows, and say something about a higher step general case. And maybe I should have said of step at least 2, because if the step is 1, so it's actually a torus, and the manifold is a torus, and we have elliptic kind of system. And then we had horocycle nil flow and smooth area preserving flows on surfaces. And this we'll go back, we'll discuss today a bit. And in between, we also said that there are also linear flows. I'll talk also about them today a little bit more. Linear flows on flat surfaces, we'll discuss this today. And these are related to billiards in rational polygons. And we also said that they represent a different type of examples, that these are somehow uniformly parabolic. These are partially parabolic. And those are non-uniformly parabolic. And I thought we had an idea of the difference between uniformly and partially last week. And this one are a bit in between, because sometimes they are considered elliptic with singularities. But I like to think of them as parabolic. And we'll discuss them today also, singularities. OK, and before I move to the new topic of this week, today, I also want to make a comment about, maybe I put it on the side because it's not the main topic. So last week, for time changes of horocycle flow and time changes of nil flows, we proved mixing, and we proved mixing via shearing. And I commented that this is a very typical mixing via shearing. This is a technique which is very important to study many type of parabolic flows. And what I wanted to add to last time is that actually there's very similar arguments to what I sketched last week in lecture 3 to prove mixing for time changes of Heisenberg nil flows. They also have been used in a parabolic setting. So I wanted to make this comment. So there is some, it exists in the elliptic case, but it's actually quite rare. So let me comment on this. So let me say, take the following example. So let me take a linear flow on the Tn, on the n-dimensional torus. So this is something like T maps to x plus T alpha, where alpha is, x maps to, I add some irrational vector, so I'm assuming it's irrational, so that the flow is equidistributed. And this is another example one can show easily is not mixing. And again, you can do it in a similar way like we did last time. You can find the Poincare recession, which is going to be a rotation on the torus dimension n-1, and the return time will be constant. And like we saw last time, this forbids mixing. But there is a work by Bassam Fayyad. The paper is titled Analytic Mixing Reparametrization of a Flow on T3. So again, you can do it for n is equal to 3, but you cannot do it for less than 3. So actually, what you can do is there exists an analytic even, not a trigonometric polynomial, but it's a series, analytic time change of this linear flow on T3, which is mixing. So I wanted to mention this result because somehow the way that mixing is proven is very similar. So the tool is also some mixing or technique. Proof is also some mixing via shearing. So also here one can kind of do the time change sufficiently oscillatory so that some curves stretch and become equidistributed because they shadow the trajectory of the flow, which is unperturbed flow, which is uniquely ergodic. But this is somehow very rare. So this is very rare, but this is a rare phenomenon. A rare phenomenon in this elliptic world. And actually it's only possible when there are Liouville rotation numbers. So in this case, you can see flow on T3. On T3 is new flow on T3 is a special flow over a rotation on T2, which is very Liouville. And so we are not in the amphitheater Yokos anymore, but actually the rotation number which is used in this base dynamics is a famous counterexample of Yokos. And it's a rotation number which is very Liouville, so it's actually measure 0 and very not generic. And the denominators of the continuous fraction of the two coordinates grow very fast and alternate very fast. So it can be achieved exceptionally. One can use mixing via shearing even in this elliptic domain. And this paper of Bassam Fayyad is before all the examples. Well, it's not before Marcus, but it's before our time changes of Heisenberg flows, and it's before time changes of, it's before smooth setup preserving flows, mixing properties. Okay, so this is, I wanted to finish from last time. Okay, and also if you are in T2, you cannot do it because the time change of irrational rotation is always, a smooth time change will never be mixing. And this can be seen as a consequence of work of Kochergin, for example, or also Katok. And okay. Good. And now I wanted to move to the new topic of today. So today I want to talk about renormalization. And again, I realized indeed that I put in the title of this course the word renormalization in parabolic dynamics. And again, this can have misleading behavior, because indeed there is parabolic dynamics in complex dynamics, and renormalization in parabolic dynamics has a very precise meaning for people in complex dynamics. And so, disclaimer, the type of renormalization we are talking today is not a complex. It's a general concept. So before, and I want to give you a very basic and baby example, but just to, as a disclaimer, renormalization have different meanings in different fields, not only in mathematics, but also in physics and even in quantum field theory. People talk about renormalization in statistical mechanics. They talk about renormalization. So we are, first of all, in the mathematical world of dynamical systems. And even then, different areas of dynamical systems use the word in a different way. So first, very, very vague. I will say very, very heuristic. So the idea, so OK, we can do it for a flow. Or we can do it for idea of renormalization. It's huge. You can want to say something about flows and something about maps. And somehow systems which are renormalizable or can be studied with renormalization have some form of self-similarity or approximate self-similarity. So this is used to study systems. We'll give examples, but let me just first be a vague introduction, which are self-similar, like a fractal, or approximately self-similar. Approximately such, maybe not exactly, but approximately. We'll see what this means. And the other idea in renormalization is that if you have a system with some built-in self-similarity between different scales, between different time scales, so, OK, we're going to study flows or maps. So we want to say the long orbits somehow have some self-similarity, maybe with an inflation, compared to short orbits. So the idea of renormalization is to rescale or zoom to study different time scale. So in this case of the flow, we want to introduce some family of renormalization operators. So renormalization flow somehow, let's write it like this. And this renormalization flow will have the property that it rescales time, so that long trajectories become short. OK, again, this is very vague, but be patient for a second. So, and in the discrete case, when I have a map, another way to think of renormalization, I have a map in my space, T, and I kind of look at smaller scales. So R in this case is a renormalization operator. And this is obtained by inducing, by, let me first say, zooming in at smaller scale. So what does it mean, zooming in? It means, for example, inducing T on a smaller part of space. For example, by consider the first return. So I take a point, and I wait until I'm back. So you have first return map ty, and then rescaling the space plus rescaling, so that the space, for example, has again, I don't know, measure 1 if you start with an invariant probability measure or some form of. OK, so this is very vague idea, but I want to show you concretely some simple examples. So how are we doing with the boards? This one can go to the bottom, so I can use the second. Good. OK, so first of all, we go back to the examples that we have from last week. And I hope you're OK if I'm talking about horocycle flow and geodesic flow. But if not, it will be limited to this example today. So last time, we said the horocycle flow. And this time, I really don't want the time change. I want the homogeneous flow. The horocycle flow, we said, satisfies this important relation that we played with last week. If I take the companion flow, which is the geodesic flow, and let's say on a compact surface, hyperbolic surface, on the unit tangent bundle of a compact hyperbolic surface with negative curvature. You can be much more general than that, but OK. And also lattice and finite volume is also fine. So it satisfies this commuting relation that we saw last time. And we used a lot in mixing via shearing and other phenomena. And we already said that this is some kind of rescaling. So imagine that I take a long trajectory. So let's fix a domain. Let's consider S in 0, 1. And let's move T. So if I fix S in 0, 1, and I take as big T e to the t, then I can take a trajectory of length big T. So let's call it gamma T of x. So this is HS. Yeah, actually, we can write it like this. H T of S of x for S between. OK, now let me just write it. H. I need another letter. H tau. Tau is 0t. Yeah, if I have a long trajectory, so this is H t of x, which is H of e to the ts. Yeah, I'm going too slow maybe, but. So this one, if I apply the geodesic flow to this trajectory of length, this is a trajectory of length t. And when I apply the geodesic flow to this trajectory of length t by this relation, I am going to get a trajectory of length 1 of the point gt of x. So x moves to gt of x. And I'll call this point y. So if I apply gt to this trajectory gamma t, is also a trajectory of horocycle flow, starting at y, which is a point at gt of x. So maybe let's say by star, by this commuting relation. So this t is fixed, but as s goes between 0 and 1, so this one spans the time between 0 and. I'm not able to do that. Oh, sorry. I think it was my phone who spoke. OK, it's a trajectory of length 1. OK, so this is an example where you can say that actually the geodesic flow, so gt, if I set, let's say, RT to be gt, this is what is a renormalization flow, in the sense that it takes the long trajectories for the flow that I want to study and shrinks them to trajectory of length 1. And in this case, everything is happening on the same space. So the same hyperbolic surface, unit tangent bundle of a hyperbolic surface is the space where the flow that I want to study act, the horocycle, and it's also the space where the renormalization act. So I can just think geodesic shrinks trajectories. The only thing is trajectory of a point x is mapped to a trajectory of another point. So this is gamma 1 of y. But OK, and you can kind of think that the horocycle flow has a built-in self-similarity. So this is a case where, OK, apart from changing the point that you want to study, but there is some kind of a long horocycle trajectory behaves like a, or is the image under renormalization of a short horocycle trajectory. OK, so this is the first example. And let me give you a second example, which is also even easier example, but it's going to be the paradigm for what I want to do today, which is linear flows in higher genus. So let me go back to another example that we saw last week. We saw the cat map. So let me recall you. So if I take this matrix, and I take the two torus, this gives me a diffeomorphism of the two torus by applying the matrix A and then taking the result mod Z2. So instead of writing the formula that we did last time, I will draw the picture. So you take the two torus, you apply the matrix A. Is this color OK, visible? Yeah. So there we can take a base. So this goes to, did I do the wrong picture? OK, something like this, 2, 1, 1, 1. OK, so you can apply the matrix to the unit square, the fundamental domain for the torus. It goes like this. And then you can actually chop and reassemble these pieces. I can all draw them back inside the square. And you can translate each of them back by a translation. So you can take the result modulo Z2. So I can translate each piece. So this is, for example, piece 2. This is piece 1. This is piece 3. And this is piece 4. And the combination of linear action and cut and paste. So mod Z2, you can think of it as a cut and paste by translations. Sorry, I go slowly because we'll go to a generalization of this example today. Translations. So something like x goes x plus v, where v is in Z2. So let's see, how am I doing? Maybe I'll erase the horocycle flow. We already understand that. OK. So, and this, now I'm going to take, so this is a hyperbolic flow. We mentioned it last week in the first lecture as an example of the most hyperbolic Zenanoso flow, which has a contracting and an expanding direction. So we said that it has eigenvalues, lambda 1 greater than 1, and lambda 2, which is 1 over lambda 1 less than 1. And the VI are eigenvectors. And I'm going to look now as a companion parabolic system. I'm going to look at the linear flow in the direction of the expanding eigenvector. So let me call it phi r be the linear flow in direction v1. So if you want, it's the solution, to make it fancy, the solution of x dot is equal to v1. So on this flow, I'm just taking points and moving them on lines in direction v1 and using the identifications of the torus to. So, okay. So you're just moving on a straight line in direction v1 with unit speed. OK, so I claim this is, OK, this is actually an elliptic flow. So it's really an example. There's no divergence. Everything is isometric. So, but we are going to, in a second, move it to higher genus. So when we're going to go from genus 1, from the torus to higher genus, it will become a prime example of parabolic flow. It will be actually this elliptic with singularities that I want to consider as a parabolic example. And OK, so in this case, again, simple to see in this case, I can take a long trajectory. So if I take, let me take in this case t to be, or let's call it tn. This time it's a sequence of times. I cannot take any t, but I can take t of the form lambda 1 to the n. So these are exponentially growing times given by the expanding eigenvector. And let me call it gamma tn will be some trajectory of length tn. So I take some point, OK, and I 0 less than t less than lambda tn. So I'm using today this notation for trajectory. So now if I take, I think I need to find some space to write. So so I want to say that if I apply the inverse of this diffeomorphism, CA, so the inverse will shrink this trajectory and bring it to a length 1 trajectory. Let's see. I think we can erase the hand-wavy renormalization idea. So let's see if this works or not. Maybe not, because the horocycle is covering, but we can try to do this. OK, let me try. Sorry, a bit of board gymnastic. OK, sounds good. And maybe we pull this up too. OK? So again, I'm thinking a very simple example now. So this is also a case where we have some form of self-similarity, but again, maybe for discrete sequence of times. OK. So as I said, how I chose it, I made it in the expanding direction. So when I look at the inverse, it will contract. OK. So let me write. If we apply, maybe I will write as R. I will take this time as a map. I will take CA inverse, so the inverse of the cut map. And then I will say that CA inverse maps my trajectory gamma CA inverse CA minus n. So this is Rn, maps this long trajectory to a trajectory of length 1. It will be some trajectory gamma 1, not of the same point, but of CA minus n of x. So again, I change the point, but a long trajectory contracts to a trajectory of the same flow. So this I'm just saying that yeah, if I take something of length lambda 1 to the n, and I apply this CA minus n, it will shrink this this is length tn, and it will shrink it. Here I'm using the inverse, the one over each other there. OK, this goes to length 1. OK, so this is another example somehow of self-similarity between trajectories of the same flow. And we'll have to modify it a bit in general. So this is, again, very special because it's somehow a self-similar direction, because I'm exactly choosing the eigendirection of the expanding map, of the Anosov map. OK, and maybe let me record for later use, because now there's an easier way to see this to 1, 1, 1. You can do it in 2 steps, because for the higher genus, I will use this breaking down into steps. I can see it as a product of 1, 1, 0, 1 and 1, 0, 1, 1. So this is A, and let's give it a name. I'll call it P plus and P minus for parabolic up and parabolic down. And each of them, so P plus and minus, they correspond to diffeos. They're just linear diffeos in this case. And each of them is just a then twist, actually. So I don't know, this is P plus. And so you can think of it as a shear, and again, modulo cut and paste. So then you can, let me some more space. Yeah, I think it was, so if I apply 1, 1, 1, I can get a sheared square, and then cut and paste to get, again, a square. And you can check that this gives a homeomorphism, so a continuous map. It wouldn't work if I had chosen a partial then twist, if I had chosen something which is not integer here. But because I chose an integer, it's continuous, and it's also a linear map of the torus. OK. And similarly, you have the other one. Sorry, the other one will map it up. OK, and so I can do it in 2 steps, as CA is the composition of C plus composed C minus of 2 then twist. OK, and another remark for later. These are all very elementary, so I'll try to be didactic. But the other remark is that I could have chosen to rotate my square so that the direction I want to study, theta, becomes vertical. And then the action of this cut map would be given by a diagonal matrix. So maybe that's, maybe this is a very elementary remark, but again, it will be useful for building intuition for later. Remark 2 is that if I rotate, so theta becomes vertical. So I'll draw some picture like this. I don't know. So theta was somehow slanted, so I don't know, something like this. It's always a square, but I rotate it so that my linear flow is vertical. And then in this coordinate, in these coordinate, rotated coordinates, x and y, then I have the action of a, so R acts by a diagonal matrix. So acts by lambda and lambda 2, or 1 over lambda. And this I want to write it as e to the, I want to write it as e to the t half, e to the minus t half, which is my gt, but let's call it t0. And for t0, which is log of lambda 1. OK. So I can think of it as a diagonal map, which in my case, maybe I did the opposite, huh? Yeah, maybe I did the opposite. I think it should have been lambda 2 here and lambda 1. And this is my matrix, if I'm doing, no, R, no, wait a second. R, we said, is the one which is contracting the vertical and expanding the whole. So R is the inverse of the cut map rotated. The cut map was expanding V1, and now I rotate so that V1 is vertical, so the inverse is contracting. So yeah, so this is the opposite of what I said. OK, this has a minus, right, correct? So this is lambda 2, which is 1 over lambda 1. And this is lambda 1, and this is e to the minus t0 half, and this is e to the t0 half. And this is, I forgot what convention I used last week. Probably this is gt0. OK. Good. OK, so very simple example. But now I want to take this as a starting point to go to higher genus. And let's see what's the best. Maybe we change board. It's OK, right, if I go to this one? Good. OK, and as I said, I want to stay today with a very simple examples, because it's nice to have concrete, very explicit examples. And I want to explain, on this example, I will try to explain a phenomenon in higher genus known as deviations of ergodic averages. And I'll try to explain it using renormalization. But it's again, I want to choose, I'll tell you later the more general setting, but I want to stick to the most simple, the simplest example I like, or I know I can do, in which you can already see the key phenomenon. So the example I want to go on to now is a higher genus example. Higher genus, and I call it toy model, because it's, I'll tell you in what is special, and I'll tell you in what it is not special. And again, I will take, well, we were in a square in genus 1, so if I want to go to genus 2, I take octagon, so O would be regular octagon. And S, or maybe I will call it also SO, to remember that it comes from the octagon, it's the surface that I obtain by gluing opposite parallel sides of the octagon by a translation. So again, maybe I need colors. So I'm going to take pairs of opposite sides and identify them by the unique translation, which maps one to the other. Okay. So on this we get a surface. So I will write it O modulo tilde, where tilde is, again, let me not write, is, OK, that's right. Glue, identify opposite parallel sides by translation. Identify opposite parallel isometric sides. Isometric is obvious in the picture, by translations. And on this very simple surface, there is a well-defined notion of linear flow. So I claim that I can just take a point and I will fix a direction, theta. I will choose it specially in a second, but for now you can define it for any theta. And you can flow using the gluings. Okay, maybe I go here, maybe go here, then I go. Okay, you can use, every time you go out, you come back using. Okay, so let me give it the same name that we had before. I forgot what I used. Phi. Let's say phi r is the, maybe I will keep the theta so we remember. Phi r theta is the linear flow in direction theta. Again, you can write an equation, a differential equation. Maybe the derivative is cosine sine. So, and we move with unit speed. And again, it's well defined on the surface if you don't hit vertices. So it's not going to be defined everywhere, as in the torus. Maybe I put remark or warning, is that it's defined almost everywhere. So it's defined on a full measure set with respect to Lebesgue measure, defined if no vertex until, or maybe defined, defined for all time, for every t, if no vertex is hit. So if you take a trajectory which goes into a vertex, you don't define what happens next. And if you want, you can draw it on the surface. And what will happen that actually this vertex, maybe we don't have to pay so much attention now, but the vertex gives rise to some kind of saddle for the flow. So at the vertex, there are several trajectories which come in. OK, so maybe we'll remark on S. Or it has, actually in this case, one saddle point. OK, maybe it's not so important now. OK. So again, more in general, the right object, we will keep to this example, but in general, more generally, the right object, the right type of surface on which you can talk about linear flows, are so-called translation surfaces. So I don't want to give formal definition, but very simple model is that every time I have a polygon, so I have a P polygon, or also a union of polygons, or union of PI, so maybe I write it like this, surfaces which you can write as taking this joint union of some polygons, modulo tilde, where PI are polygons. And you assume, it's not a given, you assume that pairs, sides of these polygons with pairs of parallel sides, parallel isometric sides, identified by translations. So you need, if I want to use translations to do the gluings, I can only glue things which are parallel and isometric. So I assume that for every side, like in the octagon, there is another side somewhere on one of the polygons which is parallel and isometric, and the gluing is by translation. And why do you need to glue by translation? This doesn't go more up. You need to glue by translation if you want to define, so then linear flow, so maybe the notion of direction, so direction theta makes sense on the whole surface. So if I have a polygon, I can always talk of, in R2, I can talk of lines in direction theta. But if when I glue sides, I use a rotation, for example, then the notion of direction would not make sense on the surface. So it's important to glue by translations to have a well-defined notion of direction theta globally on the surface. And then once you have direction theta, I can study linear flows. Linear flows are well-defined. So these are geometric structures. Translation surfaces are some kind of geometric structure on surfaces where you essentially have a flat Euclidean metric with some hidden conical singularities coming from the vertex. But I don't want to enter into the theory of translation surfaces. And I'm very happy to stick for today to the octagon as a very concrete example of a translation surface. OK. And now these linear flows, once we are in genus 2 or above, they are really parabolic, or they are elliptic with singularities, but they really have parabolic features. And OK.
Quick question.
Yes?
These polygons, is it important that they are convex?
That they are?
That they are convex polygons, or can you? No,
it's not important, but you can even have, you can even draw examples with holes, for example. You can, a nice example of a translation surface, you can also just take a square with a hole and glue opposite side. So actually, with some technical issue that I lied under the carpet. It's important, though, that when you take sides, when you glue them, so you can orient your boundary of each polygon, say, clockwise. And it's important that the sides that you glue always have opposite orientation. So for example, it could happen that I have a polygon where I have a side, and then again, the same side with the same orientation. This is my polygon. And if you want to, you could glue by translation these two. But then actually, you don't get a translation surface. You get something which is called half translation surface. So there is, so in this case, you should think that actually you glue them with opposite orientation, but then it's a rotation by pi that you are using. So you're translating and rotating by pi. So in this case, the notion of direction is also well defined, but I didn't stress it. Maybe oriented. So it's important that it's not only the direction, but somehow, yeah, it's really the direction. It's not only the line, it's really the oriented line that you want to make sense so that you have a flow. Because on this object, you don't have a well-defined flow. You have a, yeah, foliation by lines in direction theta, but it's not, it may not be orientable. Okay, but this, okay, that's a small detail. Okay, good. Okay, so why did I choose the octagon? The octagon of all translation surfaces is my personal favorite translation surface, because actually I worked a lot on the octagon, studying, for example, symbolic coding of these linear trajectories. And with John Smiley, we have a very nice symbolic characterization via substitutions and acidic language. So it's a nice example to study, but it's a nice example because it has a lot of symmetries. And this is something which was discovered by Veitch. Okay, so let me tell you in terms of renormalization, it's nice to renormalize the linear flow on the octagon because it has a fine automorphisms. Okay, so let me show you first. It has something like the cut map for the linear flow if you choose the direction properly. So let's do this. So maybe I will, for example, not example. So I will consider, and I will call it P plus in analogy with the torus, but it's upper triangular matrix, but here it has 1 plus square root of 2. And don't ask me why there is this number. I will tell you why in a second. And now I want to draw a picture that I like to draw a lot. Today I thought I'd try to be as concrete and modern. Okay, so let me look at the regular octagon. Let me draw horizontal diagonals here. And let me draw, let me draw a grid. It's an auxiliary grid, and I'll tell you. It has somehow the same role that the picture of the cut map that we still have over there of the square grid. But it's not really a grid. I'm going to draw this trapezoid, which is on top, and another copy. So these three trapezoid are, okay, let me just draw the grid. Then I'll draw 3 rectangles, like the central one. And then I'll draw again 3 trapezoids. Okay, so this is just an auxiliary grid to help me draw the next picture. And now I'm going to draw, so this is my original octagon O. And now I want to apply the matrix P plus to O. So P plus is a diagonal matrix, so it performs a shear. And I claim that I can draw the sheared octagon. So I want to draw you P plus of O. And it's nice to have this grid. Okay, horizontal side, say that I can take this as a fixed point arbitrarily. I can fix this. This is origin. This doesn't move. So this side moves, shears, and I claim that it goes exactly here for this 1 plus square root of 2. Then, wait a second, no. It actually goes here. Sorry. And this other side goes here. Okay, let me draw. I take this vertex, and then I take these 2 vertices, and these 2 vertices. So this is the sheared horizontal side, which gets up to there. And here, hop, 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 hop. So this yellow region is an octagon. Not a regular octagon, but it has 8 sides, 8 vertices. And I claim that it's exactly the sheared image of my regular octagon. And okay, I'm not going to prove this, but somehow this number, if you should do some trigonometry if you want to do, or another way that you can say, you can think that there are some cylinders. There's a cylinder here and a cylinder there, topological cylinders in my surface, and each cylinder has a modulus, the ratio of the height by the width, and I'm kind of doing a simultaneous then twist in 2 cylinders. Okay, maybe this is too much topology. If you don't know. So nevertheless, yes, you can do trigonometry. It's an exercise which I don't want you to do. So trigonometry, and actually this 2 1 plus the square root of 2 is something like twice the cotangent of pi over 8. And, okay, so I really get this type of shear octagon. And I can actually do like I did before. I can chop. I want to use this grid to reproduce each piece in one of these, for example, okay, maybe. So this piece is already inside. This piece, maybe I'll change color so we can see. Okay. I'll have a break in a bit, but maybe we finish this example and say a few more things, and then I'll have a short break. So 2 lies in this trapezoid, so it's here. So I can translate it there. So this piece 3, I can translate it here, 3 by a translation. 4, I can translate it here. 5, I can translate it here in the center. 6 is this triangle here. 7 is this here. 8 goes in the lower parallelogram, the lower trapezoid, 8, and 9 is a triangle on top, and it's this little triangle here. So what I'm saying that if you apply PO and then take the result modulo translation, so cut and paste by translation, you can translate these pieces back to the original octagon, and you get diffeomorphism. So you get actually, okay, you should check that this is continuous even, but it is. So psi, let's call it psi plus, from O, actually let me write it from SO to SO, is an obtained composing composing P plus action plus cut and paste by translations, is an automorphism of the surface. Is an actually it's an affine automorphism of SO. Okay, so I'm just and you can okay, this is just it's a parabolic, so it's a okay, parabolic is not in the it's a okay, diagonal matrix that I'm using P plus. So this is not a hyperbolic automorphism. So but what you can do, you can repeat, for example, in direction pi over 4. So you can take the octagon, and this time look at direction pi over 4. And you see here too, you have a similar picture rotated. So rotating by, or conjugating by the rotation of pi over 4, I can get some P minus. So I can get another parabolic element which now shears in direction, keeping fixed, which fixes, that one was fixing horizontal, which fixes pi over 8, pi over 4 direction. And now you can take the product. I will use the same notation for the torus, P plus, P minus. So the product of these two matrices, I guess I also wrote it, but maybe we don't need it, but okay, if I find it, I write it. Where is it? Yeah, you can multiply the two matrices, I know. Okay, you get a matrix, which I don't find now, so I will not multiply the two. Okay, you get some matrix, which is actually hyperbolic matrix, which I mean, it has a one eigenvalue greater than 1 and one eigenvalue less than 1. Okay? And this matrix, and I get associated some psi A, which is an affine, maybe I will write it SO. So this is the group of affine differs. Affine differs of SO. So, and okay, and again, if I look like before, if I look at psi theta, which is a linear flow, in the direction of the one of this eigenvalue, in direction of V1, which is the Perron-Frobenius eigenvalue of this matrix, so the largest Frobenius eigenvalue, A is a positive matrix. Actually, I think we could have written it. Oh, it's annoying me that I don't have it, but it's okay. Well, okay, it's something. Okay. Perron eigenvalue this, and this is again is renormalized exactly by psi A inverse. So if I take a long trajectory of this linear flow, like in the cat map, I can rescale it by the inverse to a short trajectory of this linear flow. Okay, so maybe I'll take a few more minutes, 2 more minutes, and then we have a break. So somehow you will have realized that this is very special choice of a direction. So, so first of all, there are other affine differs of the octagon, and this is indeed what Veach, so I'll say 2 more things and then have a break. So Veach proved that the group of affine automorphisms of this surface obtained from the regular octagon is actually generated by, no, sorry, I think I have to take, you can take P plus and P minus, sorry. Is that okay? No. So it's generated, if you want, by P, I call it Psi minus and Psi plus, or if you prefer, you can take one of them and the rotation by pi over 4. That is also an isometry of the octagon. So in particular, it's also an affine automorphism. And indeed, this is somehow as large as a group of affine differs of a translation surface can be. So it's somehow the linear parts form a lattice in SL2R, and this group is always discrete. So somehow this is, so maybe I will just write this. SO is what is called the Veach surface. So it's a very special surface rich of affine symmetries. Okay, and somehow, okay. So I can do this trick for all directions which are fixed by a hyperbolic element in this group. But actually, if you can take for almost every direction, maybe the linear flow is not exactly rescaled. And actually, this almost every can be made precise. So everyone whose tangent is not in Q square root of 2. This is kind of special arithmetic property of the regular octagon. And this square root of 2 is related to the square root of 2 we had in the matrix. But maybe, maybe there exists a sequence, Psi n, affine maps with unstable directions, hyperbolic. Sorry, hyperbolic means it expands one direction and contracts another, with unstable and the direction theta n, such that theta n approaches theta. And so maybe I cannot use the same automorphism to rescale trajectories, but I can use a sequence. And the sequence Cn can be used to renormalize the linear flow in direction theta. Okay, so I think it's a good moment to stop. So after the break, 5 minutes break, I want to explain, okay, we have this renormalization. First I could tell you, maybe I'll tell you later, how it extends to, for example, also other translation surfaces which don't have affine diffeos. There is a way to renormalize the space of translation surfaces. But what I want to tell you in this basic toy example of the octagon, why renormalization is important to study parabolic features such as deviations of ergodic averages. So I'll try to sketch the phenomenon of, I will state and sketch deviations of ergodic averages and prove it using the action of these affine maps in the special case of the octagon. Okay? We have a break. Yeah. So I'm happy to answer questions in the 5 minutes. Did I lose everybody or not? Not yet. So I have to put this back. Yeah. It's okay. Yeah. This is a break. So okay. So as I said, I want to explain why this renormalization of trajectory is helpful in this example toy model of the octagon. But first, before I go into that, let me say again, so far we only saw that there are special directions on this special, very regular surface, which are normalized, so long trajectories become short. And then I told you, okay, if I don't have a trajectory which is exactly fixed by one of those hyperbolic affine maps, and those are actually countable direction. Nevertheless, I can approximate it with a sequence of such maps. And maybe let me make a comment. Okay, I'll make it here because then we'll erase it. So maybe it's a much more general in reality. So if I take, remark, if I take another translation surface, which is not as regular as the octagon, so imagine just a small perturbation of the octagon. So you can perturb so that parallel sides opposite sides stay parallel and isometric. So maybe I can make, let me draw 4 sides, A, B, C, D, which are not of the same length anymore. And then let me reproduce them, D, C, B, A. So this is a non-regular octagon. So it's still an O' octagon. And still there are opposite parallel sides which are isometric. And so I can glue by translation. And I can get S prime, which is O prime modulo gluing. So it's another, this is a typical translation surface of genus 2 with one saddle, okay? And in general, so warning that in general, if I look for affine diffeos of this surface, if I search for affine diffeos, this will be identity. Okay, it's not empty because identity is still there, but there will be nothing. So in this case, you may say, okay, then the octagon was so special, it had affine diffeos, but if I just change a bit, okay, nevertheless, no problem, because instead then renormalize on a fixed surface, renormalization somehow, in general, in this case, but it's still renormalizable, but linear flows in almost every direction. So for almost every direction, if I look at the linear flow, I can still renormalize it, but are still renormalizable, but not by an automorphism. Not by automorphism, because, well, I don't have affine automorphisms, not by affine automorphism. So what you can prove in general is, you can find that there exists a sequence So it can be, it's approximately self-similar, or approximately, it can be renormalized by, I cannot come back by a hyperbolic map. I don't have an automorphism which stretches my trajectory, but I can come back to a nearby surface. So I can, there exists a sequence Sn, which are, let me call it, let me call it On modulo tilde. So there's a sequence of surfaces such that On converges to O, and this say in R2. So I can find, to O prime, sorry, I'm already starting from. So I can find a sequence of deformations which are very close to my original. So I can find a modified surface, and I can find a map from O prime to On, and a sequence Psi of affine. They are not affine maps from which direction do I want to go? Let's say from S prime to Sn. And somehow you can use which are hyperbolic, which are hyperbolic, and such that theta n, which is the expanded direction, most expanded direction, converges to theta. So you cannot renormalize exactly, but you can renormalize approximately. And maybe I'll have one word to how do you get this. So this, maybe one word on where these automorphisms come from. And OK, maybe we will erase our I hope you don't forget this. Maybe we'll try to. Look, I cannot put it down. Can I put it down? Yeah, I can put it down. Good. Better. So we don't have to erase the. OK. So what you can do, you can look at, as a class of dynamical system, you can look all linear flows. I'm a bit lying on translation surfaces of genus 2. Maybe I should also say with a unique saddle, but OK, let me not do it now, of genus 2. So I look, and you can imagine that those are all given by some irregular octagon with opposite parallel sides. And you can consider the following renormalization operator, which is just in the plane in R2, acts by diagonal. So GT given by e to the t half, e to the minus t half. Or maybe did I have the minus, or OK, whichever. Maybe like this. So what am I doing? I'm dilating and contracting. Sorry. OK, sorry. Rotate theta so that it becomes vertical. So if I'm interested in studying, I'm interested in studying a certain flow, I can first of all rotate my surface so it becomes vertical, and then I can start contracting the flow direction vertical and expanding the horizontal. But this you have to remember that you are always allowed modulo cut and paste. Otherwise, it would be completely trivial deformation, cut and paste by translations. And this is actually, has a fancy name. This is the Teichmüller flow. This is called, this deformation is called Teichmüller flow on the space of translation surfaces. And the fact that I can renormalize every direction, it's a theorem of Howard Mazur and William Veitch from the 80s that tells you that this deformation is, this renormalization is recurrent. And by this, I mean that, okay, I cannot tell you, I wish, but this should be a course in Tecmuller dynamics, but so for almost every linear flow, and almost every, we should define a measure on them, but you can think that is correct actually if you take almost every octagon. You can take a full measure by Lebesgue measure of choices of 4 parallel sides that you use as to determine an octagon. 4 pairs, you can choose these 4 pairs randomly with respect to Lebesgue measure on R2, and the direction randomly with respect to Lebesgue. And this is typical for almost every linear flow. Sn, which is Gtn of S, there exists a sequence Tn going to infinity such that the surface which I obtained by deforming and cutting and pasting converges to S. And vertical direction, and okay, and the okay in R2, so the vertical, okay, okay, maybe I went too far. So I wanted to say this class of linear flows on is renormalizable, but it doesn't mean that each point has a renormalization to itself, but somehow the family has a renormalization. So maybe I renormalize and get something nearby. I don't get exactly the same. It's not self-similar, the flow that I want to study, but it's approximately, say, similar. So I can almost come back to something nearby. Okay. Okay, so this is as much as I want to say about the normalization. Now you tell me, okay, why? What do we need it for? What do we need this renormalization for? So why is it useful? So why is it useful? So, and actually it's useful for many things. But for example, so one thing that I don't want to talk about, but I will just say it now. It's useful to put, because we have someone who works on Diophantine approximation in the audience, let me say that it's useful to put something like Diophantine conditions on linear flows in higher genus. So in genus 1, somehow, if you have a flow which is not periodic, you can ask how well approximated trajectories are by closed orbits. And these are, on the rotation number, on alpha, these are Diophantine conditions that tell, or arithmetic conditions, arithmetic, Diophantine or arithmetic. In genus 1, they are arithmetic conditions. And somehow this renormalization and how well recurrent this renormalization is a good way to impose Diophantine conditions in higher genus. And if you're curious about this, I do advertising. I'm giving a talk at the next ICM, which unfortunately, as you all know, it's virtual. It was supposed to be in St. Petersburg. And the topic of my ICM talk will be exactly Diophantine conditions on higher genus flows using renormalization. So if you're curious about this, the talks are recorded. You can watch them online. So it would be the 11th of July. You can watch on YouTube. I don't know if it's YouTube, but on the Italian Mathematics, you mean on the, okay. You can watch on the ICM the talk. So I will not talk about today. And the other thing is, for example, for explaining deviations of ergodic averages. So if you have a good renormalization, if you are renormalizable, and this actually works for, I will tell you which of the examples we encountered last week are renormalizable at the end, or if not, tomorrow. So, but today I will do only a baby case. So let me recall you last time that if I have a flow which is uniquely ergodic, this means that I can look at the ergodic integrals. So I take a function from, I don't know, so let's write x in general. And I take a function from x to r, which say it somehow depends which structure I have on S. If it's a manifold, I can say it's smooth, if it's smooth manifold, or a continuous, or whatever. If not, just measurable. Actually, maybe let's just take measurable since we're so general. And uniquely ergodic, it means that there exists an invariant measure, mu, unique invariant measure. So it preserves a measure mu. And I can look at the ergodic integrals of a point. So this is the integral from 0 to big T of my function along a trajectory of the flow. So these are the ergodic integrals. I'll use this notation ET for the integral along the trajectory of x of the function f up to time t. And I know by unique ergodicity that if I divide them by t, this converges to the integral of this. And this is for every x, or every x for which the orbit is defined. What I want to show you today, so as an example of application of renormalization, so maybe I will, so let's show, and actually I will show for what? So I will show, oh no, maybe not say that. So I will, sorry. So I will show, I told you, anticipated last week, that often these ergodic integrals, these quantities have polynomial behavior in parabolic dynamical systems. So they behave like t to some power less than 1. So what I want to show you this fact for the special case that we have. So let's show, so let me take S is this octagon surface, regular octagon surface. This is a toy example. The regular octagon surface, and the psi, and theta direction fixed, expanded, most expanded. So the Perron eigendirection most expanded by some psi from S to S, which is hyperbolic affine differ. So this setting that I was having here, I have my regular octagon. I have some hyperbolic differ, which is obtained by, for example, composing two twists. So I have a parabolic element like this. I go back to the octagon. I do a parabolic element in another direction, like pi 4. And the product, like the cut map, it's hyperbolic. So it has one expanding and one contracting direction. And I'm flowing exactly in the expanding direction. OK? OK, it's very special, but I disclaimed the explaining it. It's much more general than what it seems. But it's a good toy model for me to explain deviations without any technical technology to build. Otherwise, we would have to introduce Lyapunov exponents, Ozeledes eigenspaces, Kontsevich-Zoric cocycle. I don't want to do any of this. I want to keep very, very basic example where everything is concrete. OK, so I just want to show that if I take this flow, and what can I tell you about F? I'll not tell you much about F, so I'll tell you more about F later. So let's take, let's say C2, and maybe support it outside of the vertex, outside the neighborhood of the vertex. But I'll tell you, I will actually lie and not really do this case either in full, but OK. But I want to prove that these integrals for every x, OK, for almost every x, for which the flow is defined in the future forever, Okay, so maybe let me say that I take the function to be, sorry, there's more. Okay, so what is the setting? Surface, what is the measure? Mu here is just area. It's just area in R2. So mu is, the measure is just area because it's invariant under the linear flow, so it's my invariant measure. And I want to show that this one grow like t to the alpha, where alpha is a constant between 0 and 1, strictly between 0 and 1. So if the function is mean 0, it means that the ergodic average is, when I divide by t, I have to go to 0. And this power is less than 1, so when I divide by t, I actually go to 0. Okay? So this is what's called polynomial deviations. And here, if I want to put this, is actually a very old phenomenon which was discovered by Zoric, Anton Zoric, in the end of the 90s, actually. And it gave rise to the Kontsiewicz-Zoric conjecture. And it's funny to talk about this here because, of course, there is Maxim Kontsiewicz somewhere next door. But actually, I'm following a bit of, so this example of the octagon is a very special case, but that I made up for the lectures. But somehow I'm following something in between. And Forney proved, I'll tell you later what is the result, or tomorrow if I don't have time. I'll tell you what they really proved. But it's a baby, maybe let me stress, I want to do very baby case of what Zoric discovered and what Forney proved as Kontsiewicz-Zoric conjecture in 2002. And then I'll tell you also some recent extensions in which I was also involved, but small extensions, but okay, fine. So my goal now is to show you renormalization in action and how it helps to study, for example, these ergodic averages and their deviation phenomena. So what we're going to do is to build, so basically we have this automorphism, which is a hyperbolic, my renormalization, and the inverses contract trajectories, and the forward iterates build longer and longer trajectories. So I'm going to use essentially the action on homology, but I'll tell you more precisely. I'm going to use this automorphism to build longer and longer trajectories, which I control well. And this matrix will govern, and okay, let's get to that. Okay, sorry, that's okay? Good. So let's see. So the result we have in mind, again, I'm considering a long trajectory, and I want to study the ergodic integrals. But instead of taking any trajectory, I will first build some special trajectories, which I control well. First, I will not prove. So I only want to focus on deviations. So you can actually show, and this I don't want to show, you can show that phi r in this context is uniquely ergodic. So I will not prove that it is uniquely ergodic. It's, again, a baby case of a much more general result by, so again, it's a baby case of Mazur criterion or Kerckhoff-Mazur-Smiley theorem, Mazur's criterion or Kerckhoff-Mazur-Smiley theorem. So essentially, almost every linear flow in the proper sense, so for almost every polygon, almost every direction, it's uniquely ergodic. So unique ergodicity I'm not showing you. I'm using, even that one can be used. Renormalization can be used also to prove unique ergodicity. But I want to focus on deviations of ergodic averages. OK, so I will fix a basis of, and I will call it gamma 1 tilde, gamma 2 tilde, gamma 4 tilde of, OK, okay, maybe I'll be much more concrete, but let me write it like this. Of the homology, okay, maybe I started to, let me start more concrete. Given by trajectories by the following, given as follows. So what I'm going to take, I'm taking my octagon. Maybe I will draw it, no, let's draw it straight. I'll take my octagon. And maybe I will draw, so my flow is in some direction, I don't know, here. So this is the flow direction that I'm studying. And let me take some transversal direction. So for example, I don't know, let me just draw some diagonal which is transverse to my flow. So take, trajectories, and I'm going to call them gamma 1, gamma 4 from section. Let's call it sigma. So I take this section of my flow. It's a diagonal. Just take any diagonal which is not in the flow direction. And I want to take a trajectory up to trajectory from section back to section, back to sigma. So these are first return. So first returns trajectories. So let me draw the picture. It will be much more clear. So there are 4 sides, right? 4 sides. And they claim that there are 4 ways topologically in which a trajectory can come back. For example, if I take a point under this side, this side is glued to that. So if I take any point here and go to the side, it comes back here. So this is a way that the trajectory can come back. And this I call gamma 1. So gamma 1 is not a closed trajectory. It's just a trajectory from the section back to the section. And it's like the basic return. And I can't find other, or maybe gamma 1, maybe what should I call this gamma 2. So I have space for gamma 1 to be here. So gamma 1 is take any point which hits the first side. This I will call gamma 1. It comes back here, right? So this is another way that I can come back, and topologically they are not the same. And then I can take, okay, another point which hits the third side. This comes back like this. This is gamma 3. And the last one is, I need another color, maybe purple. And the last one is like this. So they correspond to the 4 sides that I can hit, okay? Okay, so these are trajectories, gamma 1 from section sigma back to sigma, first return trajectories. And it's clear it's one for every topological way that I have to come back. And now, if I want to take even a base of, maybe if you prefer, you can take a base of pi 1 if you want. If you want to make them a base of pi 1, I can just, they're not closed, but I can close them along the section. So I can choose this as a fixed point, some p, I don't know, and I can do a loop that goes to gamma 1, does gamma 1, and then comes back to p, right? So then I will say, so let gamma I tilde be the closed loop obtained closing this flow trajectory gamma I along the section, inside section, inside sigma. So again, you can imagine what is 2. So again, I start from P, I go along the trajectory, come back according to gamma 2, and then close up, and so on for the others. So, okay. Tuck, tuck, tuck. So then these are the basis of the fundamental group, and also of the homology with integer coefficient. But again, it's not any base. It's a base which is well oriented in the direction of the flow. So apart from this tiny piece, it's not so tiny now, but when we're going to stretch them, the section will become smaller and smaller, and these trajectories will be very long. And somehow the majority of the loop is just a trajectory. OK, now what do? I fix this. And now this will be my basic blocks to generate long trajectories via renormalization, via my. So now I will take, so let me call them gamma ni. So these are trajectories. This will be psi to the n. Psi, I call it psi. Psi is my my hyperbolic map of the my hyperbolic diffeo. So I take my trajectories in the flow direction, and now I'm doing some kind of inverse renormalization. I'm doing the diffeo which stretches the flow direction. So this is psi of psi of gamma I. Yeah. I call them, yes. So I take them and I stretch them. So how do they look? Maybe I'll draw some kind of. So you should imagine that I have a very, very stretched octagon. OK, then I can cut and paste it back to the octagon. But before I cut and paste it, if this is a n of my octagon, this is very stretched in the direction I want to study. My section, OK, maybe even more stretched. So my section became, it was red. My section became much shorter, and my trajectories are very long. So they're long returns. OK, so this is gamma 1 to the n, and this is, I'll just drop 2. This is gamma 2 to the n. So when I just apply them on the stretch. But remember that they don't live on the different space. They are actually also trajectory on the original octagon, because I have a diffeo. But if you look at them on the original octagon, they are very long. So that's each of them somehow is a very long trajectory. So they are stretched, and they are somehow, there are some kind of privileged trajectories that I want to control through renormalization. OK, and then again, you can close them up similarly, gamma I and tilde, you can think of them as given by, this is the action on homology of gamma I tilde. This is some action of the diffeo on homology. OK, so I want to record this action by homology. And OK, and if I just do one step of this renormalization, so I can find a matrix B, which will be a 4 by 4 matrix. So it's in SL4 with integer, actually positive integer entries. It's a kind of a change of base in homology. So I want to write the new trajectories as combination of the basic ones. So I do one step, and there will be a matrix such that gamma 1 I is, sorry, let me write with the tilde, but you can do it also without the tilde, is the sum in J from 1 to 4 of B I J gamma tilde and J. So this is somehow, no, sorry, 0. Yeah, so this is somehow write new loops as a combination with positive integer coefficient of the old loops. And correspondingly, also these curves, and correspondingly, okay, these are closed curves. So when I compose them, you can think I go one and then the other, but the part on the transversal somehow cancels. Okay, now maybe let me not do this. Okay, correspondingly, maybe let me do this. I can do it at the level of integrals. So if I look at the integral over the curve gamma 1I of my function. So this is a way to say the integral from 0 to, no, I'm saying it wrong. Okay, no, sorry, I'm going ahead of myself. Okay, okay, no, I'm too fast. Okay, okay. Now let me say it like this. So this is the level of curves. So the new one are a composition of given by this matrix B. And maybe a remark, actually, also we record that B is actually symplectic matrix. Okay, maybe this is not so important if you don't know what it means, but because it preserves intersection form in homology. So, and if you have a symplectic matrix, actually, it has, let's say, let's call V1, V2, V3, V4. It has 4 eigenvectors. This is my example, and in my example, so with eigenvalue, so you have a one eigenvalue. It's a positive matrix, so it has a Perron eigenvalue which is simple, so lambda 1 greater than lambda 2, and then it has eigenvalues. Okay, in this case, it has eigenvalues. Lambda 3 is 1 over lambda 2, and lambda 4 is 1 over lambda 1. So the symplectic gives you that the eigenvalues come into pairs. So every time you have an eigenvalue, you have 1 over the same. So the top is simple, the bottom is simple, and in this case, you also have a lambda 2, which is between lambda 1 and 1, and then you have to have 1 over. Okay, so it has 2 positive and 2 negative. Okay, so somehow what I want to do now is to use this matrix given by the action on homology of renormalization to understand how integrals along these special curves grow. Okay? Okay. And somehow we'll reduce the problem of studying integrals for the special curves to linear algebra, to studying eigenvalues and eigenvectors growth for this matrix. Okay. Oh, sorry, I erased a nice picture of the curves, but hopefully you didn't forget it. So remember, we have these special returns, the special first returns, and by renormalization inverse, so by stretching them, we get a sequence of special longer returns. And now, okay, so now, so by induction, okay, let me do it. By induction, so then we have that gamma tilde n I is, I have to multiply bn ij gamma j, so j from 1 to 4. So this is the nth iterate. So I multiply by matrix to get the next one. And now let me say, so if I pick start, instead of starting from 0, start from some n0 sufficiently large. Too bad that I erased these returns. So I had these special returns. And the special returns, the special trajectory. So in principle, if my function, if I change the point, so if I consider the integral over gamma n j, sorry, I want to say, so this is one point and one way that it returns. If I change the point a bit, the integral along this curve, in principle, changes. But if I start from a very small interval and my function is continuous, I'm going to lie and say that whatever point is under some side, I want to say that the integral up to this type of return is constant. It's a given constant. I'm assuming that my function is locally constant in some scale. It's not, you have to, it's not, I'm really lying, because but it's a baby case which I want to do first. So start from n0 such that, you know, if I integrate my function along a trajectory of a point x from 0 to the length of gamma nj. So I have to take a point where x is such that the trajectory of length, how do I write it? The trajectory of length, maybe I'll just write it like this. I'm introducing, well, the trajectory of this length is basically isotopic to gamma nj. So I want to say that all of them, all the ones which hit the same side of a stretched octagon are locally constant. So this is almost by continuity of f. Okay, I cannot move f. I cannot move the point beyond a vertex, because then the function may change abruptly. But within, if I don't hit a vertex, I'm safe by moving a little. I have the same return. So I assume that all of them are equal to some value that I will call some value of any point. They are all constant and equal to some value that I don't know. I will call rho I. Okay. So I imagine that my function is essentially locally constant, and maybe I don't start from 0, I start from n0, but I will recall n0 is equal to 0. Okay, then if I look at the integral over one of these trajectories, gamma nj of f, this is a notation for the integral of f along the trajectory I'm considering, that this will be a linear combination from 1 to 4 of bn times the integral. Okay, replace 0 with n0. So I'm starting like n0 was constant already. So this will be the integral over gamma tilde, I, sum of j, and this is f. And these are constant. These are my rho j. So this is like applying the matrix Bn to the vector rho and looking at the entry I, where rho is the vector rho 1, rho n. So I'm picking. Okay. So what I'm showing is that, what am I? I'm showing that my integrals along the special return curves, the special return trajectories, are basically governed by linear algebra. If I start from some values that are constant when I move the point, the next ones are just given by applying a matrix to a vector. Yes?
In the approximation of integral by continuity,
yes?
Blackboard, you're doing it there for the gamma j n.
So do you want me to? No, sorry. So I choose n. No, it's n0. Okay, maybe you're right. I forgot an index. So we can do it like this. Sorry, this is n0. So I find an n0 very large. Yeah, if it's true for n0, then it will be even better for the next. But you're right, I'm just doing for n0, this is for n0. And here, if you want, I don't need to replace with n0. I can just put n0 here. It's OK. I can put n0 here. And it's the same matrix. So if I apply it from, so maybe it will be n minus n0. Sorry. Yeah, so maybe that's the. So I start from n0 and go forward. But I wanted to avoid to have to be n minus n0. So let me just call and 0, call it 0. I start from there, and then I just have a Bn of, OK, so fine. So somehow, you see, I'm just renormalization gives me this way of studying ergodic integrals recursively and building them using the action on homology. And yeah, and now it's a linear algebra question. So now I will also lie a bit. Yeah, I have not so much. I'll try to finish in 5 minutes, but I'll have to. OK. Then I will tell you generalization tomorrow. But I want to try to finish this sketch today. So OK. So I'm almost there. So then again, it's a fact. So it's a fact. Maybe one can show from the assumption that the integral of the function is equal to 0, one can show that actually, so now I basically want to understand how this Bn of rho grows. And rho is some kind of, they are integrals of the function up to some returns. So rho depends on f. So f somehow determines rho. And if the function is mean 0, I claim, so I'm interested in how rho projects on the eigenvectors, because I want to know how fast this grows. So I care if it projects on the positive or negative or which of the. And you can show that actually rho is orthogonal to V1. So V1 is the Perron eigenvector, the largest eigenvector. And maybe I can, just not to leave you wondering. So for example, say that rho is exactly equal to V1. So that this coefficient that give you the integrals of the function are really the entries of the first eigenvector. Then you can prove, so V1 is a Perron eigenvector, Perron-Frobenius eigenvector. So all entries are positive, strictly positive. So you can prove that the integral of f over one of these curves is actually greater than the minimum of V1j times the norm of Bn. So each time I pick a positive amount, but this will go to, OK, maybe I'm going too much. And from this, you can prove that actually, yeah, maybe I'll skip one step. So you can prove that 1 over the length of the curve times the integral over the curve of f goes to plus infinity. It's strictly positive. OK, you can. It's a contradiction with it. It's a contradiction with the fact that the integral is 0. So somehow, if the integral is 0, you cannot project on the first eigenvector. So rho is a linear combination of V2 and possibly V3 and V4. So, and this is where somehow the worst deviation I will have come from how fast V2 grows. So the integral over gamma n j of f is less than, yeah. Sorry, we forgot something here. This was OK. It's less than the norm of Bn of rho I. Sorry. It's less than. It's less than the entry I, which is less than the norm of this vector. But this vector projects on the second eigenvector, so it grows at most like lambda 2 to the n. So it grows like the second, not like the first. And now I have to So this is for special curves, but then you have to kind of interpolate for other curves. But okay, let me first show you that this is a power deviation. But at the same time, but if I want the length of the curve, which is what I want to call t, the length of the curve is actually growing like is a linear combination of also the lengths. The curves are kind of, the lengths are also combined by juxtaposition. So it also grows like, okay, maybe with some error from the section, but like the length of the basic curve J. So what I want to show that this is maybe constant times the norm of the n. And this grows, the norm grows like the first exponent, lambda 1 to the n. So the lengths grow like the fastest exponent because it's, okay, take the max of those, and it's the length grows like the norm of the matrix, which grows like the Perron Frobenius, but the integrals grow like the second. And now we are done, because you take alpha such that alpha less than 1, so alpha less than 1, such that lambda 1 to the alpha is equal to lambda 2. So this lambda 2 to the n is actually lambda 1 to the alpha to the n, and this is t to the alpha. So this is, I'm using that order, because this is t is of the order of lambda 1. So you see the power deviation appearing. Okay, so we haven't, I think I'm out of time. So this was for special curves, just one word. Just one word, I will not even write it. If you have another trajectory which is not special, you can decompose it into this special trajectory. And maybe if you want, I can tell you more, but maybe it's not the most technical part. So maybe let me just say other trajectory, decompose them. There is a good way to decompose them. Decompose them into special return trajectories. And interpolate. And somehow you can study them. I can study also the intermediate integrals by approximating them by the special ones. OK. So I think it's what I wanted to show you for today. So this is, again, a very baby case, but it's a way to show how renormalization can be used. So again, to summarize, we just looked at the toy model of the linear flow on the octagon, which is exactly in a direction which is really renormalizable by self-similarity. So we have a diffeo which stretches trajectories or contracts trajectories. And we use the action of this diffeo in homology to construct ergodic integrals, approximate ergodic integrals of long trajectories by a linear combination of these basic returning trajectories. And then somehow we reduced our problem of studying deviations of ergodic integrals to linear algebra. And yeah, yes?
How does one know that the eigenvalues lambda 1 and lambda 2 are different?
Sorry, in this case, it's a specific example. So I was taking, then in this case, you can just, you can compute them and they are different. But so in general, maybe tomorrow I will continue from here tomorrow. So I will tell you what is the general result that has been proven by Horn and Zorich in this case. And in that case, in the typical linear flow case, then actually this exponent has to do with Lyapunov exponent of the Teichmuller flow, and in that case, simplicity, so that the fact that the second is actually this goes back to Veitch. So it's already Veitch who proved that typically you have an exponent strictly less than 1, but then in reality there are G exponent, there's a deviations, polynomial deviation spectrum. And this was Forney, who showed that there are exactly G exponents that can appear. And then it was Avila and Viana who proved that they are actually distinct G numbers. And that is some simplicity of a Lyapunov spectrum. But OK, maybe I will not do any of this in. I will just say something tomorrow about the general case and state a theorem that is the general case. Yes. So my plan for tomorrow is, again, I'll start saying a few more words about this, and then I will move to another phenomenon, which is, I want to explain obstructions to, OK, I'll tell you tomorrow. So I want to go back eventually to nil flows, though, tomorrow. We'll go back to nil flows, and I'll tell you tomorrow what we do. I want to say, OK, thanks. Yeah.